Thank you for joining us for today's online event organized in partnership by the Smith Institute and Gurobi Optimization with a guest presentation including Portchain. We're very much looking forward to discussing how optimization can help you find the most impactful solutions in the face of great uncertainty. You'll be hearing from Dr. Robert Leese, the CTO of the Smith Institute, Dr. Jakob Blavaand, Director of Mathematics at the Smith Institute, as well as Dr. Michael Lindahl, Head of Analytics at Portchain. Dr. Kostja Siefen from the Gurobi technical team will help to moderate the Q&A session and the panel discussion. Now I'd like to introduce you to Robert Leese, CTO at the Smith Institute. With over 25 years of experience in dealing with optimization problems, Robert's areas of expertise include modeling telecommunication systems, performance modeling, discrete optimization and computational complexity, consulting for companies such as Vodafone, Unilever, Cadbury Schweppes, and Ofcom. He holds a bachelor's and M.Math in mathematics from the University of Cambridge and a PhD in mathematical physics from the University of Durham. Thank you all for participating today. I will now pass it over to Robert.
Welcome everybody. My name's Robert Leese. Thank you to Blair for introducing this session. And I'd like to add my own welcome to all of you for joining us this afternoon to look at decision making in the face of uncertainty. I'm going to make a few introductory remarks presently, and then we'll have two case study presentations from Jakob and from Michael, followed by a panel discussion. So I hope, as well as seeing some examples of optimization techniques in action to address these difficult sorts of questions, we'll also have a chance to discuss questions of interest to yourselves and your own organizations. What I'd like to do first of all is to make a few introductory remarks about the sorts of tasks that are involved in making decision making under uncertainty and carrying out these difficult sorts of calculations that underpin tricky decisions. There we go. Okay, so forecasting for decision making is a key part of the whole enterprise here, and what I'd like to do is just to give you some brief introduction to the elements of what makes for a good outcome. This diagram simplifies things somewhat, and of course in a real development situation the solution would be reached with a process of some trial and error, some iteration, but when you've finished and reached a successful conclusion, you should be able to see the following key elements in the chain of tasks that you've put together. These involve data, first of all. Next, they involve a model. So by a model, I mean the framework in which you can think about or analyze the situation or system that you have to deal with. The third element is the optimization part. This is where the data and the model are brought together in order to create the analysis that ultimately leads to decisions. And decisions, of course, are where the value in this whole process is crystallized. So really we should think of data and modeling as being parts of the input to this process. Optimization is where value is created, and decision making is where that value is made apparent. The impact of uncertainty on this process arises really in two broad ways. First of all, there's uncertainty in the data, and secondly, there's uncertainty in the model itself. And it's perhaps important to keep in mind that there are two sorts of uncertainty. The first is to do with uncertainty in what we can measure or what we can forecast, and the second is uncertainty in what we know. And both of those can impact and need to be taken into account when we optimize and make decisions. I'll just say a little bit more by way of introduction about those four different elements. As I said, data is making use of what we can measure or what we can forecast. And that might involve, depending on the application, things such as the size of the tasks to be undertaken, things like the loads on a system or the demands for services, that sort of thing, might well involve, typically will involve, data about the resources that are available to carry out those tasks. So issues such as the price of materials, staffing costs, availability of resources. And crucially, the data also often involves observations of system performance. And that might be quantitative observation or qualitative observation. So I think if you in a situation where you need to carry out analysis in order to make decisions, you probably have a fair idea what data it is that you're bringing into that process. What are the quantities that you can measure or forecast and then take forward in the analysis? Let me say something about the model. As I said, the model is where we make use of what we know. It's where we capture the system interactions and processes. These might be well known from prior experience, but I think increasingly in a lot of modern applications, system interactions and processes are highly complex, even in physical systems, but certainly in social systems and economic systems, systems with large numbers of interacting components. Those processes can be difficult to understand and difficult to model, and are themselves a significant source of uncertainty. The next element in models are the constraints on possible actions. So what are the constraints on cost? What are the budget constraints, for example? What are the constraints on time? What deadlines do we need to be working to, or what time horizons are we making decisions over? What are the materials or other resources that are available for use? All of those need to be built into the model in some way so that the solutions that we come up with as a result of the optimization turn out to be feasible. The third element in the model is always something to do with the objectives. What are the performance measures on which decisions will be based? In other words, what issues are the decisions trying to address? That needs to be considered and built into the framework that the model creates for doing the analysis. So those are all issues that we need to take part and need to take account of in the modeling stage. The third element that I want to say something about is uncertainty. How does uncertainty impact the data? How do we see that uncertainty is present, either in the data or in the model? Well, in data, we may see that some of the data is missing, or it might be incomplete. So that is not so much a lack of knowledge about the future, which we might be forgiven for. This is a lack of knowledge about the present or the past. Okay, but it's very often unavoidable. Data sets are not generally nice and clean and organized for purposes when they're gathered. Missing or incomplete data is the norm. We need to take into account measurement uncertainty. So data may have been gathered under imperfect conditions, even if it's quantitative data. Other types of data may be observations that are themselves subjective, may depend on the conditions in which they were gathered. So that those issues add an extra element to the uncertainty that we would see in data. And then, of course, there's the uncertainty in forecasts. This is uncertainty in future values of data. Remember, we're making decisions in order to make a better future for ourselves. The data that is relevant to that is data that will apply in the future. It's data that relates, say, to future weather forecasts, or future climate, or future sales projections. Okay, those are inevitably subject to uncertainty. That's probably the major source of uncertainty in data. Just turning to the uncertainty that's present in the modeling process, there may be uncertainty about future available technologies and resources that needs to be accounted for. There's often process uncertainty, the processes that are under which the system works. that govern what happens in the system, how it evolves. It could be to do with the efficiency of processes. Maybe we know roughly what the processes are, but we're not quite sure how strong they are. An example might be what's the rate, what's the R number for a disease, propagation of disease, for example, that's been so much in the news recently. We may not we may know what the process is, but be uncertain about what its parameter values are. Or it may be something much more fundamental. We may just not know how the processes should be described. The processes may be so complex that we don't really yet fully understand how they should be modelled, and that's an uncertainty in itself. And then, of course, there's uncertainty on the constraints on possible actions as well. I just want to wrap up this introduction by coming to the last part of the chain, which is the decisions themselves. And they may be automated. So, for example, if a decision is being made regularly and holds the consequences of that decision may hold for a relatively short period of time, after which the system is updated again, then that might be effectively an online control system. Those decisions can be automated. Longer term decisions are often taken offline and often include other policy objectives as well. So it may be that a decision needs to be signed off in order to create organizational policies and need to be treated at board level or senior management level inside an organization in light of the available evidence that the optimizations have been able to shed light on. We need to be clear about what the decisions are designed to achieve. And I've given some examples here. It may be high performance in normal operations, maybe satisfactory performance at low cost, avoidance of high cost extremes in system behavior. So in other words, avoiding disaster. It may be decisions in order to increase resilience to disruption so that systems can recover when they move too far out of norm. Or it may be the avoidance of variation in behavior or performance. And this would be something that is particularly present if we've got systems that might induce bias or some sort of unfairness in how they treat people. We want to make sure that that variation in those sorts of systems is controlled. So decisions can be very varied. The objectives are often competing. In other words, there are trade-offs. If you improve one of these objectives, very often you do so to the detriment of another. That means they need to be considered together. I'm going to finish the introduction just with two further elements of what I would consider to be good practice here. First of all, uncertainty should not be seen as an excuse for lack of clarity about the objectives. And finally, the observation that models and optimization can highlight how uncertainty propagates through the system. And that is, in essence, what we're trying to do here. The uncertainty in data and in models needs to be propagated through the optimization in order to inform good decision making. Good, so that's where I'd like to wrap up the introduction and hand over to my colleague Jakob Blavaand, who will take us through the next presentation. So Jakob is Director of Mathematics at the Smith Institute. He has more than 5 years of experience consulting on projects across business and government. He leads on the Smith Institute's capability in optimization. He holds a BA and MSc degrees in mathematics from Aarhus University in Denmark and a DPhil in mathematics from the University of Oxford. So Jakob, I'll hand over to you. Thank you.
Thank you for the introduction, and thank you to all the participants for coming today. What I'll be talking about today is just an example of how we can address the uncertainty that we see in our forecast and how we can use that to make better decisions, to unlock some business value. So let me take you on a journey, starting with, this is Jess, and Jess is the manager of a building complex. she's looking at the operational costs of running this building, and particularly she is looking at the cost that they have associated to the electricity bill every month. She thinks it's quite high, and she's noticing that there's quite a lot of variability in these costs, and primarily driven by uncertainty in the price and volatility in the price of electricity. So she's wondering, could I maybe lower my costs by installing a battery? Not an alkaline battery like this, but sort of a proper industry scale battery. In this way, I could use, I could buy energy when it's cheap, and then I could sell it when, or not sell it, but use it when it's when the price would otherwise be expensive. And once I have a battery like this, I could also start using it for other things, like helping the system operator in their with their goal of managing the electricity grid, because their job is to keep the balance between supply and demand. And in order to do that, they need to have access to very fast-acting reserves, such as batteries. And by giving access to part of your capacity, you'd get a reward for that. So the first two, where you're shifting the load, you're buying energy when it's cheap, and you're using it when it would otherwise be expensive to buy. That can reduce your costs. But by using the service, by providing the service, you now have a revenue stream as well. So how can we combine these two things? So what she's been looking at is this forecast, historical data on price, and she's noticed that, yeah, we have these peaks, and we have troughs, and maybe we could take advantage of that. We also see that the demand that they see in this building complex is quite predictable at night. Nothing really happens. And around 5 a.m. in the morning, things start ramping up. You have your air conditioning starting up and so on, and people start getting into work, and then it gradually ramps down. So okay, so now she knows what the aim is. She wants to lower her monthly costs. What tools does she have available to us? Well, there's the load shifting, so you can shift the load. So you can also lower the peak the peak load that she's seeing, because there's a charge to that as well. And then she could provide some reserve to the grid. In order to use these tools, she has to make some decisions. This will be one of these online control problems that Robert mentioned just a few minutes back, where in this case, every hour you need to make a decision about whether to charge or discharge your battery, and at which level it needs to be set at. You also need to specify how much of the capacity you want to use for reserve. In order to make those decisions, we need some information. We need forecasts about what's going to happen in the future. Our best estimate of what the future looks like for price, for demand, but also for the use of reserve. And so that is, and so you can see these four boxes, they more or less line up with the boxes that Robert had on his previous slide. So again, as Robert said, this is the end goal of an analytic solution like this looks like these boxes, but the way in which you arrive at it is quite often in the direction that we've just talked about, from left to right. Instead, you start with your aim, figure out, well, what is the decision that you can make, and then look at, well, what data do they need in order to make those decisions? So data is sitting at the end, or at the beginning, because it's really the foundation of what we are going to do. With that historical data, you can build your forecasting models, for example, by using machine learning. So the machine learning model here can tell you about the likely outcomes of the future, but it can't make a decision for you. It's very informative about the potential for the price and for the demand, but it can't tell you what to do in that situation. For that, you need your optimization solution. And so we need to make good decisions, and therefore we're solving an optimization. So that's the setup, and these are the decisions that we need to make several times a day in this online control system. Now, Jess's main question was really, should I really invest in this or not? And that's sort of the main decision that she has to make. And so what we'll want to do is trying to explore whether it is feasible for her to invest in a battery, and what type of decision making she should use, and what value is associated to each of those. So let's look at the information that she has. So the information we have demand. You can see that this is historical demand for a month, compiled over a couple of over some historical data. So you can see that the average here is there's some clear daily trends. You have clear weekly trends as well, and you can also see that there is quite a bit of variability in the data. This, but nevertheless, the structure of the average is the same as the data itself, and the same goes for price. The capacity usage, so here expressed as a fraction of the capacity that we are offering up to the grid, and how much they're taking. That's a bit of a different story, in the sense that we would expect that that half the time the operator will ask us to load the battery, and half the time they'll ask us to discharge the battery. In which case the average is around about 0, and so the average in that case might not be a very good indication of what's going to happen. And I want you to bear that in mind for what we come and talk about in a few slides from now. Okay, so we have these we have the forecasts. Let's talk about those. So we have this time series of price. So this is going up to the to 10 o'clock on the 7th of October. And from that point on, we can make our best guess as what the electricity price would evolve like. So this is represented by the black line here. If depending on what type of forecasting model this comes out of, we might be able to generate a set of scenarios that explore the uncertainty in this forecast. But if we can't go all the way to scenarios, we might be able to get a range on each of the point forecasts instead. So basically, we're looking at 3 different types of forecasts: a point forecast, which in this case would be, for example, our best estimate of what the future would be. A point forecast with a range, with an upper and a lower bound. We expect that our best guess is that it's going to be a certain level, but it could also vary in between those two ranges. Or thirdly, you have a range of different scenarios that you look at. What type of forecast you have has an impact on what type of decision making that you can make. If you just have a point forecast, you can make sort of classical optimization. You can use that in a classical optimization setting and make decisions based on that. And that might very well be exactly what you need if your forecast is, if your point forecast is very good, is a good representation of what's going to happen. So, for example, in this case, if the mean is good, the average forecast is good, then yeah, it's probably sufficient to do that. But it's not encapsulating anything about the uncertainty. Now, if you had a point forecast with a range, then you could do something more with that. You could build what's called a robust optimization model. And if you have these scenarios, you can go even further, and you can look at stochastic optimization. And stochastic optimization, that's the path that we will go down in this talk, and contrast it to classical optimization based on a point forecast. Because you can see here that it's pretty clear that at least on the forecasting side of things, going from point to range to scenarios is increasing in complexity. And the same thing is happening in the decision space. As you move down your forecasts, your decision-making algorithms and models become more complex. So we need to make sure that there is enough benefit of using a more complex decision-making process. There should be enough value in that compared to the classical approach. So what we'll be doing is we'll look at stochastic optimization, but we'll also contrast it to the point forecasts. So let's look at the decisions that need to be made in at each time point in this control system. So again, we're starting here at our with our time series at this point, and we had our best estimate for what will happen over the next 24 hours with the price. And from if we're using a classical point forecast optimization method, that's all of the information that we would need in order to make a decision as to whether to charge the battery or not, and also to know what kind of reserve that we're setting. Now, the decision that you're making, so you're solving to make that decision, you will be solving an optimization problem. That optimization problem will give you the actions that you need to take right now. But the actions that you take right now needs to support the future that the forecast has shown you. So actually, it is solving an optimization problem and it's giving you values for our actions. They're giving us decisions that we could take for each hour into the future. So each 24 hours into the future. However, we're only ever considering the first hour, because in an hour's time, we'll do the whole process again. Because in the meantime, some of the uncertainty have revealed itself, the system has moved on. Now we have to update our forecasts. So that's what we do with classical point forecast optimization. Now, if we had scenarios that we could generate, then instead of just having a single view of the future, we could have this range of different scenarios describing what the future could look like. And the optimization that we are solving is now giving us an action to take right now that can support each of these different scenarios. So in fact, it's giving us decisions that we could take for each time point 24 hours into the future for each of the different scenarios. And they're coming together, fitting together in one action to take right now. So let's take that action and then see how the price evolves. It's a bit difficult to see on this picture maybe, but I hope you can see that there's a small purple line. So the price went a bit down, a bit further down than our best guess, but it's pretty close. Okay. And then we start the process again. If we are looking at from the point forecast point of view, we're looking 24 hours into the future. If we're looking at the scenario, the stochastic optimization, we're looking at a range of different ones. And again, we make our decision, and then the uncertainty evolves, and we carry on like that. So you can see that we're making a lot of decisions all of the time, and if we can make better decisions, these the decisions, the better value of those decisions don't actually have to be that big. But the thing is that they will be accumulating over a month. So totally, they might actually give us a significant value. Right. So at the heart of this decision making, whether it's a point forecast, whether it is a stochastic optimization, is an optimization model. This optimization model is taking into account a range of different things and bringing them all together. It is the price of the electricity, the demand from our building complex, the capacity usage from the past and forecast of that. It's parameters on the battery that we're using. Its capacity, how quickly can it ramp. It's also the market rules about the electricity market that we need to take into account. It's the size of the horizon. How far into the future do we want to optimize? So in this case, what I've just talked about was 24 hours into the future, because the data had sort of a nice 24-hour period. But that could be 2 days, it could be 3 days, it could be even an entire week. It's part of what you need to tune when you're building your model. Other optimization parameters, such as if you want to include a bit of a buffer in your battery and not use it completely in order to protect it a bit. And of course, all of that gives us the constraints and the limitations on the actions that we can take. Now, in order to evaluate those actions, we also need to have an objective to work against, and that's in this case the cost of electricity. What is the overall cost when we take the use of electricity into account, but also the lowering of the peak and the revenue that we get from using the battery as reserve. Right, so that's our model, bringing it all together. Now that we have a model, we need to implement it. And the way that we usually implement these models is, well, you have to implement it in a programming language somehow. And the programming language that we often use is Python, because it is it's a convenient tool that allows us to quickly create prototypes and models, and there is a large support community for it, and it's really useful in a data science environment, because in this application we both need to have an machine learning model that can create our forecasts. So that could be built in some in whatever data science library you want. Pick your favorite for that. And we have to have our optimization model as well. Both of them can be implemented in Python. The data we can get from the cloud or from some internal storage. And once we have the data, it's gone through the process of creating a new forecast. We build our optimization model. Then we need to find out, well, what is the decision we need to make? And that's where Gurobi come into the picture. So we send this optimization model off to Gurobi and then ask it to solve it. It returns the answer, and we take the first action that is recommended and we move on. So that's the implementation side of things. Now that we have two different approaches, we need to evaluate which of the two to go for. And given that we're dealing with uncertainty here, we need to simulate this. So what we're doing is that we're simulating a month of operation, and we're simulating a month of operation of this battery. We are using either the point forecast optimization method or a stochastic optimization method, and then we're comparing the two, comparing the costs at the end of the end of a month. Now that will only tell us whether it is stochastic or the classical point forecast optimization we should be using, but it doesn't really tell us about the overall question about should we invest or not in this. So we need to also consider two other approaches, which are to say, okay, what if we knew exactly what was going to happen? What if there was no uncertainty at all? That will give us an ideal sort of lower limit for our costs. With this specific battery, with this specific setup, well, what is the lowest that we can get? And that's sort of that can be used as a benchmark for looking at how much of the potential value have we actually arrived at. And at the other end of the scale is, well, if you don't have a battery at all, what is that going to cost you? And so you have your no battery, you have your perfect information, and somewhere in between, this point forecast and stochastic optimization are sitting. So if we simulate these monthly operations, a lot of times we can get a good indication of the value of these different things. So let's go and look at that. So here we're looking at the value of the stochastic solution. So what I mean by that is that we've taken the monthly costs that's generated when we're using a stochastic operation scheme, and we're looking at the difference between that and where we use the point forecast. If you have a positive value here, that means that the stochastic is better than the point forecast. And you can see that the average on this is about £2,000 in a month. The lower part is the value of having a battery. So here we're looking at the difference between operating without a battery and when you have perfect information on this battery, or perfect information about the future. And combined, we can see that with perfect information, the value that we can get is about 15,500 a month. Now, stochastic optimization achieves about 90% of that perfect information value, whereas the point forecast method achieves about 77%. That's a relative improvement from point forecast to stochastic, about 16 to 17%. And one of the reasons for this difference to occur, or the reason why we're seeing these spikes there in the graph, in the histogram, is that there are certain that the stochastic optimization is protecting better against some relative low probability situations that have a high impact. But because we are, although you have a low probability of an event occurring, because we're making decisions again and again in a almost continuous fashion, those rare events aren't actually that rare anymore, and therefore has a significant impact. So by taking your machine learning model and not just using the point forecast, but really using it to create scenarios based around the errors in the forecast that it's creating, and therefore coupling the two tighter together, we can actually gain some value that was would otherwise be locked away. So returning to Jess, should she invest or not? Well, if we just look at what a battery would cost her, it would cost around $1 million for that, which in today's pounds, which is about 750,000. So if we look at just in terms of the expenses and just on the average monthly saving, then that battery would pay itself back in 5.2 years if we are using a point forecast, but 4.5 years for stochastic optimization, and 4 years if you had perfect information about what was going on. So now she's armed with the information that she needs. She can take that to the board and make a decision. They might say, well, that's not enough value to be gained, even with the perfect information. And then she will probably have to go back to the drawing board and say, well, what other things could I do? Maybe I could install solar panels on the roof, and then use my battery to save some of that energy for the best times to use that. In which case, you'd need to go back and change the way in which you operate your model. But the point here is that she's built up this framework for making a decision, exploring what's happening, and informing her investment decision. That is pretty easy to do so, and it gives her a lot of insight into what's going on. It's very explicit. So some of the key questions that you need to ask yourself if you want to take advantage of the uncertainty is that, well, first of all, you have to understand, well, what are the main sources of uncertainty in your business? What are their impacts? How can you mitigate these risks? And do you have the data to quantify this? If you answer these, then they'll provide you a foundation for making decisions that take uncertainty into account in an algorithmic and an automated way, as we've just seen here. But just going through that exercise would be a valuable step for you to do anyway, and just to make apparent what decisions, what uncertainties there are. You are likely to have make more robust decisions yourself, even though it might not be based on an automated algorithm. So in summary, we've seen that we can unlock some value. We can unlock value by embracing uncertainty in our decision making, and this is partly done by a tighter integration between forecast that we produce by a machine learning model and using an optimization. Part of the value comes from protecting against high impact outcomes, although they might have a low probability, and that it's always a good idea to quantify your risks. Thank you for your attention.
Thank you very much, Jakob, for a very interesting talk there. I think from the scientific end of things, it's very striking how you can keep pace with uncertainty by updating your decisions. And of course, you need the sorts of computational tools that Kostja and his colleagues at Gurobi produce in order to be able to sort of keep pace in real time with evolving uncertainty, so that you can update your view of the world and the decisions that you should be taking. I think what we've got here is also a great example of informing investment decisions. So in this case, in a new technology such as batteries, in the question, you can imagine arising at the top level of a company. When do we adopt new technology? At what point do we invest? Should we be an early adopter? Should we wait a while for the cost to come down of new technology? So to be able to make these sorts of investment decisions in a much more informed way in the face of uncertainty is, I think, a really powerful tool to be using.
So we now have the great opportunity to discuss interesting topics with our presenters, who are really experts in their fields. So today, of course, with a special focus on uncertainty, which has become even more important this year, since a lot of businesses face these disruptions. So let's see, I see Michael, Jakob, Robert. Okay, I can see you there. So why don't we get started? Machine learning, sometimes also referred to as artificial intelligence, has become very popular over the last years. Many companies we talk to have a lot of data and now have an analytics team and with data scientists, and their main goal is to find interesting and useful information in that data. And this is usually considered successful once a company has identified the right tools and algorithms that help them to find interesting patterns, relationships, and ultimately allow them to create better forecasts. Now, with the implementation of optimization into business processes on top of this, a key question is, how do you track and measure success when you implement optimization? So, Robert, do you want to start?
I can start. I'm not sure I'll have the last word on this. I mean, I think Jakob and Michael have both alluded to some of the ways that you can measure success, and that is by measuring against what you currently do. So it's one thing to chase the best possible outcome, but it's another thing to chase an outcome which is much better than what you currently have. And I think to begin with, that would be the place to look, for improvements over the present day. Don't know if any of my colleagues have got anything to add to that.
Yeah, I'm happy to jump in. So I think it's about of course, what does success look like? What is it actually that you want to improve? So for example, you might have upper level management, they want to improve profitability and reduce costs, but you might have some planners sitting further down in the organization who cares more about robustness, for example, and keeping customers happy. And I think it's really important that you also ensure that you actually capture the different ways that you want to create value. And as you also mentioned, Robert, then track those things, get some KPIs and get some numbers that you can follow, because then the numbers they don't improve like you expect, right, then you will need to use that to drive a conversation around, are we targeting the wrong thing or measuring the wrong thing, or are we not using the tool in the right way, or there's something wrong with the model? I think that's very important.
Yeah, absolutely. And so you mentioned something important here, which is the fact that you quite often have multiple different KPIs that you're working with, and if you have a human team of planners, they although they know that there's a focus on a certain set of these KPIs, instinctively as humans, we can probably only work with 1 or 2 KPIs at a time and find the best trade-off between those. Having more than that is very, very difficult, and that's where you have something like an optimization solution that can help you do that. If you find a way of weighting the different KPIs against each other, well, that can be taken into account, and you can get a more unbiased view of your operation than you can in a manual setting.
Thank you. Yeah, let's see. So there's another interesting topic here, together with a question, which is I would call it organizational resistance and internal selling. So decision support with optimization usually involves quite some process and role changes. So especially in the beginning, organizations are struggling with internal resistance and acceptance. Could you share some concepts or stories on how you can tackle this challenge and overcome this hurdle in the beginning? Maybe, yeah. Well, Jakob, why don't you start?
Yeah, no, I can have a go. Certainly, we've worked with a number of organizations where introducing a new optimization solution, either to replace something that they already have, or as an addition to what they as addition to what they're currently doing. And I think that the process that you go through is quite similar, in the sense that it's extremely important to have the end users in mind and take them on board from the very beginning. Because if in the planning room, if they don't agree at all with what's going on, then you'll never get the acceptance. And we are dealing with human beings that have been doing this job for often a lifetime. They've spent their whole career on doing this. So they're really, really skilled at it. And that's why you can also, in Michael's example, you can see that if they can achieve 85% of the best possible outcome, that's pretty good. So you want to listen to what they have to say, and you have to then provide a solution that they are comfortable with and that they can accept. If you don't get them to accept it, that there's no traction at all, and that's really important, that they are part of the evaluation of whatever tool that you build. So at the beginning, setting the requirements, but also taking them along the journey, showing them prototypes, and then at the end, in the evaluation phase as well.
So Michael, how did you manage this in your industry?
Yeah, so first of all, I very much agree with Jakob. It's really, really important to listen a lot to the end users, because they are really the experts. And also in our industry, that's usually people who are working at 10 or 20 years with planning, which means that there will always be something that they know that you don't know. And again, yeah, optimization is really about enabling them to make better decisions. So really see where should you come in and help them with maybe some part of the decision making, but maybe some of the other part of the decision making is not really it's not really something that they want to engage in. So really finding these value pockets where you really can help them, and of course also say, building a tool that also helps them get the trust in the solution. So instead of just giving them this very black box way of saying, okay, this is a fine solution, do you want to accept, yes, no? You want to really give them as much, say, context as possible. So really also explaining why do we believe that this is the best solution, give them more KPIs, give them the possibility to easily get an overview around what are the different decisions that are suggested by the optimizer. So they also can evaluate, but also can override some of the decisions that they might not agree with. And I think, yeah, finally, it's also, especially when you're starting with optimization, either if you're doing it internally or working with a consultancy company or buy something, it's just to, you know, start small and build maybe a prototype, and then see if you can get some of these early wins around, for example, just getting this deeper understanding into a business, start maybe using for some of these more strategic things and evaluating what would happen if we, for example, increase our capacity, because that might not be as sensitive, for example, to the planners and something that's really hard for them. So that's also a place where you can start a little bit smaller and get some good, some initial good value out of it.
Yeah, I'd certainly echo Michael's comments about quick wins, and also we haven't said much in the webinar about the process of model building. Well, that's a highly collaborative process, and understanding what constraints and what objectives and what variables need to be built in and which can be safely left out, and which can be which are most important, where the sensitivities are. All of those affect the complexity of the final solution and the confidence in how it's used, and it can only be done. It only can be done in a collaborative way.
So there's also another aspect to this question. So you know, we talked about the end users and the people involved with the systems, but before you get to that, you usually have another hurdle, which is you need to convince some more senior management people that this endeavor is worth it. So I mean, this question comes in different flavors. Yeah. So most of the time when you get started, this is some kind of black box technology, and people don't just want to trust some data scientists. Yeah. So it's really about gaining trust. You know, we all know optimization and its benefits from our daily work, but it may not be so clear in an early exploratory phase. And just like any other new technology, a common first question is, does this work for me? Is this feasible? Does it have a business case? Is it fast enough? Uncertainties, yeah. So I guess that's another version of that question. So how do you approach these concerns? Yeah. So how do you bring this acceptance or this positive attitude into senior management? Maybe Robert, as a senior manager.
Yeah, well, I think it's important to realize that successful companies have to innovate and have to consistently innovate. And so, you know, maybe not every company is able to sort of assimilate these sorts of techniques, but I think a lot can, especially companies that have got high ambition and high growth plans. I mean, in order to get consistent buy-in, then, you know, showing an early return on investment, doing it in a way that is transparent and well-founded. You know, the sort of example that Jakob had at the end of his presentation about how do you decide whether to invest in this battery or not. And I think also, you know, building the relationship to the point where you can advise what not to do as well as what you should do, I think builds trust as well. So I think it comes from a combination of building trust, which takes a lot of time, and also showing some real return on investment, ideally at an early stage.
Yeah, absolutely. I can only echo that. And so some of the early wins that you might get would be to take some of the very burdensome sort of labor-intensive task in the planning situation, take them out, because they're laborious, they're repetitive, and it's done over and over again. But maybe you can just create a small tool that actually has a big impact on saving those people's time. So that has both the benefit of showing the senior management, hey, this type of technology actually works quite well, and you get the buy-in from the end user because you've just saved them a lot of time. And also, furthermore, another good way is to say, well, showcase some of the questions that you all of a sudden can answer when you have an optimization model. These what-if questions that you all of a sudden are within reach of answering, but you've never really had the ability to do before. What if we change? What happens if we change the weight of these different SLAs? What if we change the way in which we derive routes that go into our route planning system, and all these sorts of things. It would previously have been massive undertakings, but if you have your optimization model and it's built sufficiently flexible, you can start answering all of those questions that are important to the senior management.
I can just very much concur, and I think a good way to get started is that every business should have some key metrics that they are very important for their business in order to be profitable. And a good way to start is by finding some of these winners. Say, okay, which one, if we could raise that by 10 or 15%, what would that mean for our business? And if you have such a metric, then the next question is then, okay, what are the decisions that are impacting and what are the constraints of those decisions? And then I think from that on, that can really drive some interesting conversation that also upper management would like to engage in.
Measurable, that seems to be a pattern here. Okay, so maybe we move over to a few questions about uncertainty, and of course that's very close to forecasting. So one common concern is usually by learning from the past, you learn the past, but the purpose of the forecast is usually a better estimate of the future. So how do you, so maybe as a first start, and there are other aspects to this topic, so how do you predict the future if all you have is data from the past? Maybe that's the one for you, Jakob.
Then the only thing that I heard was that you wanted me to answer a question, but I don't know what I'm answering.
Oh yeah. Oh, I'm sorry. I can repeat. Your webcam was a bit blurry, so probably your internet connection had a break for a few seconds. Okay. So quick summary of the question. So with the rise of machine learning and AI, the one common concern is the purpose of a forecast is a better estimate of the future. But if you look at data from the past and if you learn from the past, you learn the past. So how do you can learn from the past to make a better forecast for the future? So how to get a valid forecast?
Well, that's absolutely that's a big thing these days. Of course, I think all companies who are basing their operation on forecasts are facing these issues right now. I think here it's important that when you can see that your forecasts are off in a significant way, that you track that changes, and then you have to really think hard about whether you change the way in which you make those forecasts, how often you retrain your model, what data do you include, and potentially also include external data that you hadn't really thought about you might need. For example, with this pandemic, it might be relevant to look at external data sources on people movement and mobility data, and this something that you didn't really know that you needed before. And when you have that, well, you might be able to update your forecasting model to make better predictions. But then it's also important to look at the uncertainty. So just something simple like giving a prediction interval for each of your forecasts. You can see, well, how confident am I actually that this is correct? And if you have very wide prediction intervals, you should be a bit worried, which is something that you don't see if you just have a point forecast that you base your business around.
So, well, okay. Maybe let's add some more color to that to that topic. We also saw stochastic optimization. So the explicit, so you explicitly consider uncertainty as part of the optimization. Is that a remedy for everything? Does that help for that? Should that be used all the time, or when is this the appropriate tool?
I mean, yeah. So for that, you certainly requires that you have a good handle on your uncertainty. But part of the problem is that although if your model is predicting predicting forecasts of sales of say tickets in the cinema, say, if you are not taking into account the something that can tell you that a fundamental change has happened, that we aren't allowed to go to the cinema at the moment, then you can make a prediction that is quite certain. It doesn't have any the confidence interval isn't very big, so therefore you can't really use that in the optimization any better than you could before. So whatever uncertainty you have, in order to take it into account, it has to be captured by in your forecasts. And so stochastic optimization wouldn't be a solution to that situation. You need to feed. If your system can't see the information that's most impacting your ability to make decisions, well, then you can't act against it.
Sure.
But a classical optimization wouldn't be able to do that anyway either. So you're a bit stuck. So you have to be careful. But I think it starts with understanding your data and your forecasts.
I would ask a similar question to Michael. I mean, we've seen so many uncertainties in your slides. Like you mentioned, whatever, change of load, schedule, delays, weather, COVID. So lots of stuff. So in your application, from the standpoint of the methods that you've implemented, what turned out to work best in your case and for your end users when it comes to handling uncertainties in these planning systems?
Yeah, so the way you can say that we're handling is more you can say the simple approach, the point estimate. So we have a guess. We also indicate do some things to also indicate the user that it is a prediction. It's not an actual value. But then what we really do is then that we then say give the user the possibility to also easily override a prediction because they also have that context. If they think it's wrong, or they have some additional context that we don't have, and then finally the way that we also help our customers to deal with all these uncertainties is that allowing them then to react to these disruptions and changes very quickly. So even though that our plan will be outdated, maybe then the users can quickly update any data whenever they get new information in, and then use that to update their decisions. And that is, of course, we have also looked actually into stochastic optimization, and I think one of the things that Leese was a huge issue for us. Like one was that just the computational complexity, as some of you know, it becomes very, very slow. And what we really are aiming for is to give our users, give them some answers really, really quick we're always aiming for like within a minute, because we can just see there's a lot of value of giving them these results very quick, because it means that when you give them a result, they can start looking at them, they can validate, but they can also see if they put in some wrong data or forgot to update some of the capacity, then they can update it and run it again. So we rather, I can say, want to give the users the ability to react fast, even though we're not, you can say, fully capturing the uncertainty that there actually is in the input.
Could you just? Sorry.
Go ahead.
Just wanted to add. So the stochastic optimization, yes, there's the challenges about complexity. Certainly, you have to be really careful about how you do that, how you define your scenarios, because if you have multiple drivers, multiple different drivers with correlated uncertainty, you have to bring those together. And in order to avoid sort of a explosion of dimensions that you need to consider, you have to be quite clever about how you can limit that down. So the example that we showed with the battery, in that case, that took a fraction of a second to solve that optimization. So it really depends on what you're trying to do, and that was the number of decision variables and number of constraints were in the thousands for that. So it depends on what type of decision that you want to make, whether it's appropriate, whether it's slow, and how you deal with it. Sorry, go ahead, Robert.
Yeah. I was going to make the point that there's a distinction between systems where success really depends on what goes on the average, and systems where it's very important to get a handle on what goes on when you move away from the average into the sort of tail, especially deep into the tails of what the possible outcomes might be. So, for example, anything that is safety critical as in an application would be something where you probably want to be dealing with with some in some way a stochastic optimization in order to work out what's going on. There may well be some systems where knowing what goes on average is all you really need to know. In that case, these techniques may not be able to add very much value. But set aside that, it's not just increases in computer hardware, but also increases in modeling techniques and the computational techniques. They're just making a lot more applications available or accessible to techniques of this sort.
Introspection into risks. Absolutely. So I'm looking at the time before we get to the last question. That's a good one for the audience. Maybe one quick thing that comes up also often in that context. So we talk about learning, and usually it's there's machine learning, the AI part on one side, and then there's optimization on the other side. But and also, as with the chest example, we've seen examples where actually machine learning was used to train a computer or to do optimal decisions. So is this kind of a competition for mathematical optimizations? Are there use cases where you would always prefer the machine learning approach, or can you give a clear distinction on which tool is the right, well, which one is the right tool for the job? Jakob, that's one for you.
Yeah, I can have a go. So the chest example, or AlphaGo for that matter, is a very, very confined and controlled problem. You don't have the problems with real-world data that's extremely noisy that you have to take into account as well. So you get a more of a controlled environment where you can do a lot of simulations, and the decisions that you need to make are relatively simple. It's confined space and of opportunities that you need to make. So it's especially discrete steps that you need to take. So do you move your pawn here or there, or which chess brick do you move? when you go into a space of where it's continuous decisions that you need to make, or a combination of them, then it becomes quite it becomes more involved and more complex. And I haven't seen a good example where the thing that we would be very good at with an optimization model would be able to be replaced by some kind of reinforcement learned agent, because there needs to be some historical data that you can train it on. And also at the end, if you manage to succeed and you get something that sort of similar looks sensible, then if you start asking questions about, well, what is that actually doing? What is it fitted on? Then it's really difficult to know. Whereas if you have a model, you've written it down, you know exactly what it is that it's doing, and you can start playing with it. And you say, okay, well, if I change this constraint to be just this, change this in a bit, you can look at the results and see what impacts it have. With the trained model, you have to retrain it all over again, and that can be a cumbersome process.
Yeah, I can just I very much agree, because if you look what was really the challenge in both chess and Go, so as Jakob said, it's like every single decision you make is quite simple, as the solution space is very, very small. The hard part of both of these games is that when you then made a decision, is it then to say, did this decision bring me closer to winning or further away from winning? And that was really the challenge where you say deep learning and reinforcement learning was really made some progress in then taking one of these boards and evaluating who is most likely to win here. And because it's very hard, because in both chess and Go, you only get this feedback right in the end if you won the game or lost the game, where many business problems, you make a lot of decisions at the same time, and you'll get feedback much earlier. And one of the, I think, important thing also in the difference is that in machine learning and deep learning is that you are often trying to, you can say, redo what you did, where when you start with a model, you actually start to think around what is it, not what I don't want to do what I just did. I want to do the best thing right. I want to optimize towards some objectives that actually help me not just repeating the decisions I'm making, but making even better decisions. So I think the whole mindset around really thinking around what is it you want to achieve, and formulating your model, as Jakob also mentioned, there's a ton of value in that.
Thank you. So my original plan was to do a lightning round and ask you for your favorite optimization project, but conscious of the time, I think we really need to wrap it up. And so over to you, Robert, for some final remarks.
Okay, thank you. I'm going to have one more go at sharing my screen. You can see that. Okay, very good. I think you can see the contact details there. So that's what I wanted to make sure you had available. I mean, first of all, I'd like to thank the speakers, Jakob and Michael, for two wonderful presentations, and Kostja for steering us through a very stimulating discussion over the last half hour or so. The contact details that you hope you can see on the screen are for our respective organisations at Smith Institute, Portchain, and Gurobi Optimization. I think if I was going to draw one key message out of what we've heard, is that it would be that there's value locked away in complex systems, and that the way to unlock that value is to couple cutting edge optimization techniques with detailed knowledge of how businesses operate. We've certainly seen through Jakob and Michael's presentations examples of that in shipping and in energy. And I think it's clear that if you can embrace these sorts of techniques, then not only is it possible to improve your current operations, but it's also possible to respond to new business environments and new opportunities, and to do that by making better decisions and making them with confidence. So I think that would be my takeaway message for the day. I hope we've given you something to think about, maybe even something to act upon. I'd like to thank everybody who's taken the time to join the webinar, and I'm sure I say that on behalf of all my colleagues in Gurobi and Portchain as well. And we hope to be in contact with you again soon. So thank you very much and enjoy the rest of your day.